As we move towards the era of CBDC-based Forex, we want to pioneer a decentralized system that doesn't favor any single currency at the expense of others. We want to build an architecture that allows even the smallest of countries to onboard and participate in global financial exchange. This has led us to our proposal, CBAP, a cross-border app platform. Centralized finance works perfectly if there's only one country using a single currency. It's highly efficient, low cost, and easy to manage. But CeFi won't work for cross-border financial transactions because there's no global bank that acts as the topmost central authority that all others must obey. The most natural solution would be peer-to-peer decentralized blockchain technologies with applications built on top, as in decentralized finance, also known as DeFi. The network topology would be something like this, a distributed peer-to-peer network. However, this isn't the ideal network topology because the central banks should play a different role than regular peer-to-peer nodes. We can turn this into this. Here we have central banks in each region functioning as the nodes, connected in a peer-to-peer network. Central banks continue to play a governance role in their own territories. They work together to maintain a distributed ledger for the purpose of cross-border transactions. This sounds similar to a permissioned or federated blockchain, but we're not proposing a blockchain. It's true that there are many innovative and attractive blockchain-based DeFi concepts that have come up in recent years. But if solutions for CBDC cross-border payments continually use blockchain, there's a risk that solution providers won't be able to innovate outside the scope of the blockchain ledger. A few of the potential limitations of blockchain solutions for CBDC payments and exchange include scalability, privacy, and governance. The blockchain's consensus mechanism is the fundamental reason why blockchain isn't suited for the CBDC world. The first principle of blockchain is the trust no one, verify on your own methodology. That means all nodes need to recalculate to verify the result coming from any other nodes. The more nodes added to the system, the slower the consensus is reached. To solve this problem, we need to think outside the box. Let's see how we verify complex math computations in real life. Assume I ask you to calculate 42 factorial. You would likely pick up a calculator and key in the formula to get the result. In this case, you'll get a huge number on the screen, but how do you know it's correct? There are two ways to verify the result. I can either run such calculation by keying in the formula again in my own calculator, or I could simply check the calculator you're using is genuine and functioning properly, and observe that you used it correctly. With all that verified, I can trust the result without recalculating on my own. Blockchain chooses the former recalculation solution. We choose the latter verification solution. No doubt, our solution is much easier. The technology we use to verify is called trusted computing. Our platform defines a protocol that's flexible enough to work with any hardware that supports remote attestation. It gives users answers to the following questions on system integrity. In CBAP, central banks deploy their trusted hardware nodes to the internet where they connect to each other and continuously run mutual remote attestation against each other at random. Remote attestation verifies that others' execution environments, which we call enclaves, are trusted and free of modifications. Any malicious node that fails to pass remote attestation will be voted off the network. Because the network is trusted, and as long as correct input data and code were loaded and executed in the verified enclave, we can trust the result without recalculating them locally. This is our first principle. Verify the environment, don't recalculate the result. This mind shift is rewarded as verifying the environment in most cases is much cheaper than recalculating the result in a distributed network. Now, although all nodes are running in trusted enclaves, what if the end user double spends? Due to network latency or malicious intent to cheat, nodes may receive transactions in a different order than what was originally sent. If the nodes execute transactions based on this order, their ledger would be inconsistent. A consensus algorithm is necessary to make all nodes agree on a single sequence before they're executed, so that every ledger or state is consistent. There are many different consensus algorithms in the blockchain world. Consensus is the main cause of energy waste, POW, or potential centralization, POS, since all of them are based on some type of competition between nodes, either for natural or financial resources. Again, let's think outside the box. What's the real reason we need consensus? We just need a way to get all nodes to agree on the same sequence of transactions, right? Since we already have trusted hardware, we can trust the node's computing result as long as they have correct input. Now we can simply add timestamps to transactions. All transactions received by a state maintainer node should be attached a timestamp from trusted atomic clocks and then sync with others. When duplicated transactions are received by multiple nodes, only the earliest timestamp is kept. So all transactions will have a unique and accurate timestamp. Every node will hold transactions they receive either directly or from syncing with other nodes in a pool called conveyor for a period of time before getting executed. During this period of time, while the transactions are still held on the conveyor, all transactions will be sorted by timestamps as new transactions are inserted continuously. After the set period of time, the wrong sequence of transactions originally caused by network latency will be corrected, and all nodes can get a consistent sequence of transactions without competition. Then all transactions can be executed based on the sequence of their original timestamp. The ledger or state among all nodes is consistent. Let's see an animation of how it works. Governance and privacy are trade-offs that can hardly be resolved by blockchain. CBDC needs to maintain some type of governance and privacy that are configurable and programmable. Given that all sensitive code and data are handled inside hardware enclaves of a trusted network, no one, including the central banks themselves, can access this data from outside, unless there are predefined governance APIs to reveal the data. The transaction originator is the only one besides the involved central banks who can retrieve the detailed transaction information. They can send the transaction JSON file to any interested individual. That person can use whichever country's app to extract the transaction hash and confirm the transaction. As opposed to using a public blockchain, this setup ensures transaction privacy. Another factor to consider is that not all CBDCs will be running on blockchain or distributed ledger technologies. If the interoperable layer is chosen to be a blockchain, then that shuts out all the CBDCs that have opted for non-blockchain based implementations. Ideally, we'd have a mutual clearance layer that can interact with both blockchain and non-blockchain based CBDCs. This is our solution, CBAP, Cross-Border App Platform. This is a CBDC customized version of the T project, which we've been developing since 2019. This platform is a secure execution environment that isn't a blockchain. It's able to provide confidential transactions through hardware security. It will also be a highly scalable system that reduces barriers to entry for participating countries no matter what underlying technology their CBDC is using. Part of our design philosophy is to ensure that countries of all sizes can transact on the global financial CBDC markets with equal access. We want to emphasize the decentralization part of our proposal, as a system we're working towards will allow participating countries to conduct transactions without use of a central reserve currency. Allowing for decentralized participation will also open up doors, as a large, powerful country is no longer dictating the terms of engagement. In our demo prototype, we assume 3 central banks join such a network. They are India, Hong Kong, and Singapore. Each central bank deploys a trusted machine. These nodes are called state machines because they work together to process transactions and maintain the synchronized state, also known as a ledger. In their own region, commercial banks or end users connect to their central bank nodes. These nodes host apps that provide user interactions. End users use an app to initiate transactions that are then sent to the commercial bank node. The commercial bank node runs the government's business logic for approval. Upon approval, the commercial bank sends the transaction to the central bank state maintainer node. This is one of the 3 central banks in the network. The 3 central banks will share all transactions they receive and sort them by timestamps. Eventually, all 3 state nodes will get the same transaction and execute to update the ledger to the same state. CBAP as a platform runs like a network operations system. It loads apps into the secure enclave. In a short period of time, we developed a bunch of apps for this demo prototype, including the cross-border payment, foreign exchange based on Uniswap version 1 algorithm, and the government's and developer portal. We will demo some of the main apps shortly. Each of them have unique features, such as cross-border payments, an automatic market maker used for foreign exchange, and a government's app used by central banks to approve transactions with AML compliance. Developing CBAP apps is easier than developing smart contract-based apps due to secure hardware and the secure nature of WebAssembly. In the prototype, we don't have direct access to real CBDC. We use 3 blockchains as mock-ups in the demo prototype to simulate the different currencies: Indian rupee, Hong Kong dollar, and the Singapore dollar. 3 bridges connect those 3 CBDCs to the CBAP. Once the assets are bridged to the CBAP, all transactions will be happening between apps in the CBAP. No more blockchain consensus or smart contracts are needed until someone wants to withdraw funds back to CBDC. Bridges are customized to fit different types of underlayer CBDCs. There are multiple bridge technologies existing in the market as shown on the screen. All components in the system are interchangeable. They are connected by APIs, such as a cross-border payment app that can be replaced by existing CBDC mobile apps, or Uniswap that can be replaced by Mariana Project, or we can also use mBridge. This is the demo setup. Alice lives in India, Bob lives in Hong Kong, and Charlie lives in Singapore. Alice wants to send Bob 10,000 Indian rupees. Bob deposits 1,000 of those Indian rupees and transfers to a CBDC wallet, then exchanges 100 Hong Kong dollars with Charlie. Charlie asks Bob for proof that he received 10,000 Indian rupees from Alice first. Alice exports the proof of transaction so that Charlie can then verify locally. Now let's move on to the demo. Alice is a new CBAP user from India. To connect an Indian CBDC account, she needs to select the Goerli network in MetaMask, as we use Goerli to simulate the Indian CBDC platform. After she logs in, she will find a zero balance in her CBAP wallet, but 23,780 Indian rupees in her CBDC account. She deposits 12,345 Indian rupees to her CBAP wallet. After a few seconds, she now has funds in her CBAP account. Alice clicks cross-border transfer, pastes Bob's address here, and sets the amount at 10,000 while leaving the currency as Indian rupee. After confirmation, this transaction is pending governance approval. The admin of the Indian Central Bank logs into the governance app, reviews the transaction details, then runs the AML and sanctions list check. If everything passes, which is the case in this scenario, approval is granted and confirmed. Although Bob lives in Hong Kong, he can still log in to the Indian CBAP demo and check his balance. In this case, Bob chooses to withdraw 1,000 Indian rupees, and after a few seconds, he can see his Indian CBDC balance increase by 1,000, while his CBAP balance decreases to 9,000 Indian rupees. Bob wants to exchange some of his Indian rupees to 100 Hong Kong dollars and sends that amount to Charlie in Singapore. The process is very similar to how Alice did it before, but now Bob needs to select Hong Kong dollar in the currency list. The Uniswap app running in the background estimates that Bob needs to pay 1,060 Indian rupees for 100 Hong Kong dollars. Bob accepts and confirms this rate. Again, this transaction needs to be approved by the Indian Central Bank. As the government's approval process is the same as before, we'll quickly skip over that. Charlie leaves in Singapore because he wants to log into the CBAP Hong Kong app. He will need to use the Arbitrum Goerli network in his MetaMask because we simulate the Hong Kong CBDC using the Arbitrum testnet. He logs into the CBAP Hong Kong dollar app and checks his balance. He has received 100 Hong Kong dollars. Bob was asked by Charlie to show proof that he received Alice's 10,000 Indian rupees before making his exchange and sending 100 Hong Kong dollars to Charlie. Bob asks Alice for the transaction details in JSON format. Alice logs in and selects the corresponding transaction, then exports to JSON text. She copies this text, then emails it to Bob. Bob then forwards this JSON text to Charlie. Due to a lack of trust in the Hong Kong and Indian systems, Charlie chooses to validate this transaction in the Singapore CBAP system. He connects to the Sepolia network to log into the Singapore CBAP. He clicks the query transaction, pastes the JSON text that he received from Bob. Then the system calculates the hash of such a transaction. Now Charlie can get confirmation of transaction time from the Singapore CBAP system, which he knows is earlier than Bob's 100 Hong Kong dollar transaction. There are other apps on the CBAP available in the App Store, and developers can add more apps to this platform using the Dev Portal. TSwap is the Uniswap version 1 as a placeholder for the Mariana Project. PriceFeeder is a secure price oracle we use to fetch real-time foreign exchange rates from Yahoo. The government's apps can do more than just approve transactions. The admin can also adjust the liquidity pools or manage the state machine nodes, such as adding or removing central banks to the network. Our central bank app platform provides a decentralized financial application layer that gives equal access to countries of all sizes. It helps move countries away from depending on a central reserve currency by providing a peer network for trusted settlement of financial transactions. And unlike CBDC solutions that rely on blockchain, our platform allows for transaction privacy as well as a rich application framework more capable than smart contracts. This design encourages even small countries with limited resources to participate in foreign exchange and eventually build their own apps optimized for their emerging use cases.